Welcome back to the next video, everybody. Today we're going to be pressing on, plowing through chapter 7 of my notes. We're going to be looking at surjectivity at 3 or 5 today. So let's recall what chapter 7 has sort of been about recently. The main result of the chapter is kind of a weakening of, I guess, Sayre's conjecture. Theorem 2, it says let P be a prime bigger than 2. Let's let rho from GQ to GL2 of FP bar be a continuous, irreducible, odd representation. Suppose that rho is modular of some type, then rho is modular of the type prescribed by Sayre's conjecture. Moreover, if rho is FP bar modular of some type nk epsilon and n and p are coprime, then n is a multiple of Sayre's n, k is at least Sayre's k, and epsilon is obtained from Sayre's epsilon by composition with the natural map from z mod nz to z mod n of rho z. Okay, so we saw in a previous video that Rivets' theorem was a special case of this. All right, we're basically interested in where special cases of this result are used in the proof of Fermat's last theorem. In preparation for more discussions of such special cases, we saw last time that proposition 1, if E over Q is a semi-stable elliptic curve and P is prime, and rho bar P from GQ to GL2 FP is the residual mod P representation attached to E, then rho bar P is either surjective or it's reducible, and its semi-simplification is just 1 direct sum chi P bar. All right? And then we had a corollary to this, which was if E over Q is semi-stable and rho bar 3 is irreducible, then it can't be induced from the Galois group of Q adjoined root -3. It doesn't come from a smaller representation like that, basically. Okay, so let's do something new today. Let's use this. So let's let E over Q be a semi-stable elliptic curve. If for a prime P, rho bar P is not surjective, then by results found in Sayre's Galois properties paper, E must have a P torsion point that's actually defined over Q. And so by, for example, Silverman 1, 3.4, results found in 3.4, E has to be equipped with a unique degree P SelfQ isogeny. So a unique map from E to E defined over Q of degree P. So if rho bar 3 and rho bar 5 are both not surjective, then E admits a SelfQ isogeny of degree 15 because there will be a map from E to E of degree 3 and then another one from E to E of degree 5. How do you take the degree of a composition? You multiply the degrees of each individual map. Okay, from theorem 1 of chapter 3 of my notes, we know that such an isogeny corresponds to what? A non-cuspidal Q point of x0, 15, right? Using results from Diamond and Sherman in chapter 3, one easily finds that x0, 15, in fact, that modular curve is an elliptic curve, and it only has 8 rational points, and 4 of them are just its cuspidal points. So it only has 4 non-cuspidal rational points. Direct calculation shows that the 4 non-cuspidal points correspond up to twist to elliptic curves of conductor 50. But you can check that no twist of those curves is semi-stable, so that's a contradiction. If you want more details, you can see the tables in the modular functions of one variable 4 book. Okay, and so we got a contradiction. So rho bar 3 or rho bar 5 has to be surjective, one of the two, for any semi-stable elliptic curve. Perfect. All right, and if you go back to chapter 1 of my notes, this is one of the key results that we had kind of left unproven that I said I would do in a later chapter. Okay, what if it's rho bar 3 that's surjective? Well, then by proposition 1 above, rho bar 3 is irreducible. By Langland's tunnel, rho bar 3 is modular of type 3 to the m times the conductor of rho bar 3 squared of weight 1 over Q3 for some m at least 0. We know this stuff, though I have a whole video coming up on the level later, so don't worry about why this is true. Okay, although yeah, okay. So actually, though, we want to do better with this level. We want to show that rho bar 3 is in fact modular of type just the conductor of rho bar 3 to 1. So weight 2 trivial character over Q bar 3. If rho bar 3 is flat at 3, and of type 3 times the conductor of rho bar 3, weight 2 character 1 over Q bar 3, if we're not flat at 3. So we will do this later. I have a whole video on this level later. But to show that this is actually true, we will require the following reduction of theorem 2, and that its conditions 1 and 2 hold in the special case P equals 3, and that rho is modular of type n squared to 1 over Q bar 3, where n is square free. So here's another instance, basically, of theorem 2 that we're going to need, although it's more like a reduction in some sense. It's like a reduction, which is proven in a special case. So it is a special case of theorem 2. So I'll call this Kerios reductions. No, this is not the same as Kerios hard theorem. This is a different result of Kerios. It says, suppose rho from GQ to GL2 of FP bar is continuous, irreducible, and odd. Then if rho is modular of type NK epsilon over QP bar and not induced from Q adjoined root -1, respectively Q adjoined root -3, if P equals 2, respectively if P equals 3, then it's actually modular of type NK epsilon prime over QP bar for all epsilon prime whose mod P reduction equals that of E, and such that epsilon prime of -1 is -1 to the K. So this is the typical property that characters attached to cusp forms have. So what does this say? This says that in order to prove theorem 2 above, the main results of the chapter, you actually don't need to consider the character of the type at all. And so from here on out, we really won't. Now, there are other reductions that Kerios made. So you can boil theorem 2 down essentially to showing two different things. So I'll go into that right now. Suppose rho is modular of type NK over QP bar. Notice I got rid of the character because I don't need to talk about it anymore. Then in order to prove that rho is modular of type n of rho k QP bar, which is what theorem 2 purports to be able to do, if P is at least 3 and K is at least 2, it suffices to prove the following two things instead of proving the entire theorem 2. Let L be a prime that's not P. Then there exists a prime Q not dividing NL and a new form of type N prime Q K epsilon prime over QP bar, where N prime divides N and epsilon prime is trivial mod Q, whose associated mod P Galois representation is just isomorphic to the given rho. Okay, so you got your new form that's got a Galois representation. I want that to be isomorphic to rho. 2, there's one other thing you have to prove. If L not equals P is a prime dividing N such that L squared doesn't divide N, and L doesn't divide N of rho, so the conductor of rho, i.e. rho is unramified at L, then rho is modular of type N over L, K over QP bar. And the proof of this is in Kerios' CRG paper, which has been referenced before. All right, so how is this used? Well, we'll see this in use a couple of times, but if you use the information in the paragraph prior to the statement of Kerios' reduction above, so the slides just prior, Wiles and Taylor prove in Wiles and Wiles Taylor's papers, the original proofs of Fermat's theorem, that all deformations of rho bar 3, which are ramified at only finitely many primes, semi-stable at 3, and which have determinate the cyclotomic character are modular. So we saw this back in chapter 1 of my notes. Hence, E is modular by the fivefold theorem, since rho 3 is a deformation with these properties by theorem 1 of chapter 1. Okay. So technically, Taylor and Wiles, as we recall from chapter 1, they also actually require, to prove their result, that rho bar 3 is absolutely irreducible when restricted to the Galois group of Q adjoined root -3. But this follows immediately from the fact that its restricted image is just easily shown to be SL2 of F3 because that has index 2 in GL2 of F3. And the Galois group of Q adjoined root -3 has index 2 in the Galois group of Q. Indeed, if it was reducible, it would be a direct sum of two characters, so its image would be abelian. Okay, perfect. So a lot of this should sound somewhat familiar if you've watched literally every video in my playlist so far. Okay, so this is what happens if rho bar 3 is surjective. What if it's rho bar 5 that's surjective? And well, what if rho bar 3 isn't surjective? Well, then we know from today that rho bar 5 has to be surjective because one of the two has to be. In Wiles' paper, he shows that there's a semi-stable elliptic curve E prime over Q whose mod 3 representation, rho bar prime 3, is irreducible, and whose mod 5 representation, rho bar prime 5, is isomorphic to rho bar 5. We'll be talking about this later, I think, in chapter 16 of my notes. By the argument in the previous case, so just to port the argument we just got done going through to this new setup, you find that E prime is modular. And so by the fivefold theorem, rho bar 5 is modular of type N prime to 1 over Q5, where N prime is the conductor of E prime. Okay. Since E prime is semi-stable, N prime is square free. And here, we're going to actually use Rivets' theorem again. I think a lot of people don't realize that Rivets' theorem was used twice in the original proof of Fermat's theorem. By the square-free special case of Rivets' theorem discussed above, because I have a square-free level conductor here, rho bar 5 is in fact modular of type the conductor of rho bar 5 with weight 2 character 1 over Q bar 5 if rho bar 5 is flat at 5, and of type 5 times the conductor of rho bar 5 weight 2 character 1 over Q bar 5 if not. And so using this, Wiles and Taylor show in the original argument that all deformations of rho bar 5, which are ramified at only finitely many primes, semi-stable at 5, and whose determinant is the cyclotomic character or modular. So very similar to the above. So again, a lot of this was talked about in a little bit less detail in chapter 1 of my notes. So again, by the fivefold theorem, E is modular. Perfect. So then in any case, every semi-stable elliptic curve E over Q is modular. Perfect. So the conclusion is this, of this kind of piece of the chapter. Square-free Rivets theorem is used to prove FLT once semi-stable modularity is established. Rivets theorem is also used in the P equals 5 of the above argument. So the case rho bar 5 is surjective. Kerios reduction, along with the proof of its two conditions, in the case P equals 3 and rho is modular of type n squared 2, 1 over Q bar 3, where n is square free, is used in the P equals 3 case of the above argument. So the case rho bar 3 is surjective. So there are the 3 times in the proof of Fermat's last theorem that special cases of theorem 2 of this chapter, the first slide of this video today, are used. Okay. Kerios reduction uses a theorem of Mazur, which we'll describe, I think, in the next video. We'll also describe the proof of Rivets theorem in the square-free case in the next video, okay? Then we will describe the proof of the two conditions of Kerios reduction in our special case later, and we will also be examining these results up here where we are able to nail down the level of rho bar 3 so precisely, okay? And similar for 5. So we'll start all that next video. Thanks for watching, and I'll see you then.